In this section we will look at bifurcation theory. Bifurcation theory, roughly speaking, is the theory of how solutions change as you change a parameter in a system. In order to do this, we will consider autonomous ordinary differential equations of this form: x dot is equal to f of x and mu, where mu is a parameter, typically a single real quantity. We'll assume that f is smooth to some degree, both in x and in mu. You can sort of split bifurcation theory into two aspects. One is to show that solutions under certain circumstances behave in a very regular way, that they continue, and then to identify the points where things change, and typically they are isolated. They're called bifurcation points, and there is very good classification of them. At these bifurcation points, the number and stability of equilibria can change, the number and stability of periodic orbits, and a whole variety of other invariant sets can appear or disappear. We've already seen one result that allows one to infer when bifurcations do not happen. So suppose you have a hyperbolic equilibrium for some particular value mu star of your parameter. This means that if we call the equilibrium x star, we have that f of x star and mu star is equal to 0. If that equilibrium is hyperbolic, this means that the eigenvalues of the Jacobian df evaluated at the point x star mu star must have a real part not equal to 0, all of them. This means that the Jacobian has full rank, and one can perturb the equations by the intermediate value theorem. Under small changes in mu, we will have also a hyperbolic equilibrium that is close to x star. It's useful to express this in terms of what we call a bifurcation diagram. So the convention is we have the parameter on the horizontal axis, and we have some measure of the solution, in this case let's say x, in the vertical axis. Although note that because x may be multidimensional, one may need to take a real observable of x, such as the length of x or one of the components of x. If we consider a point, say mu star and x star, such that we have an equilibrium at mu star x star, then we have a point on the bifurcation diagram. If that equilibrium is hyperbolic, this means that on changing mu, there will be a continuation of that x star. So if you like, x will be a function of mu, such that x of mu star is equal to x star. There will be what we call a branch near mu is equal to mu star. However, this is typically not a global property, so we may have a branch here that becomes vertical and turns around. The branch in the other direction may also interact with other unstable solutions at points that we will call bifurcation points. So here's one bifurcation point, here's another bifurcation point. And the general property of bifurcation points are that when you look either side of the bifurcation point, you'll find that the number of solutions, the number of equilibrium solutions changes.